welcome everybody to our webinar for Space Weather Explorers Week. And this month of November, during NASA's Heliophysics Big Year, the theme for this month has been bonus science. And so we're very happy to have our special guest today to talk about the bonus science of the extended atmosphere of Earth. You'll be hearing from Dr. Lara Waldrop, who is a professor of electrical and computer engineering at the University of Illinois Urbana-Champaign. And she'll be speaking to you about a new NASA mission called the Carruthers Geocorona Observatory, which is a very exciting mission and is actually the funder of Space Weather Explorers Week. So this is a special confluence for us all. And again, I just want to remind you all that if you have questions throughout the presentation, feel free to ask that in the Q&A box, and we will then address your questions. We'll either address them right in the moment if it's appropriate, or we'll have some time at the end. So if you don't have any questions at the moment, we'll make sure that at the end of the presentation, you'll be able to ask all kinds of questions about this mission and any other topics in space weather that you might be curious about. So with that, I am going to say welcome to Dr. Waldrop and let her take control of the screen.
Right. Thanks so much, Brian. Well, I am delighted to have this opportunity to talk to you about my favorite NASA mission. It's one, as Brian mentioned, it's the upcoming Carruthers Geocorona Observatory. The Carruthers mission is designed to study Earth's outermost atmospheric layer. This is known as the exosphere or geocorona in our mission name. And what we're going to do is image the light that it emits with two special cameras. So in this cartoon, we've kind of depicted the mission concept that we're talking about. And in that tiny blue dot in the top right corner is meant to represent Earth. So right away, you can see just how huge we expect this atmospheric layer to be. We expect it. We don't necessarily know for sure how big it is, as I'll explain as we go on. And then also how far away from Earth that we're going to be deployed in order to capture its full extent in a single image. Now, the Carruthers mission is one of many NASA missions supported by its heliophysics program. So that you can see that circled in yellow, and then all of the missions within the heliophysics programs are all in yellow. Carruthers Geocorona Observatory there in bold indicates that it's an upcoming mission. It hasn't yet launched. And you're probably familiar with some other NASA missions and programs that are aimed, for example, at studying distant stars and galaxies. You can see that in blue. Hubble Space Telescope is among those. NASA also studies moons and planets with missions such as the Mars Curiosity rover. Those are shown in purple. And then also Earth itself. Maybe you're familiar with the Landsat missions shown in green, which take pictures of Earth's surface from space to support things like resource management and monitoring natural disasters. And then some of those are also shown in yellow. But the heliophysics missions shown, in orange. Heliophysics missions shown in yellow all have a common overarching goal, which is to understand the influence of the sun within our solar system, and particularly the sun's influence on Earth and its protective bubble known as the magnetosphere. Now, the magnetosphere is formed by Earth's intrinsic magnetic field. This is the molten iron core of Earth sloshes around, produces a dipole magnetic field, and it's embedded in the solar system. And you can see this is roughly drawn to scale, more or less, approximately how big that is actually around the Earth. What's not drawn to scale here is the sun, which is, of course, a lot bigger than what it is shown. And beyond just giving off bright sunlight, which we're all familiar with, the sun also emits a steady stream of energetic charged particles. And here by charged particles, I'm talking about ions and electrons. These are atoms where the electron has been stripped off because it's so hot. And collectively, this gas is known as plasma. And then meanwhile, the sun's own magnetic field permeates the solar system. Now, the pressure from this steady stream of so-called solar wind, the plasma and magnetic fields that propagates outward from the sun's surface, distorts the Earth's magnetic field lines. So if it worked in the solar wind, it would look like a typical symmetric dipole magnet. Like if you had the iron filings and you sprinkled them around a bar magnet, they would trace out that dipole field. That's what the Earth's intrinsic magnetic field looks like. But in the presence of the solar wind, which is constantly flowing past it, it gets distorted into this bullet shape. And one of the most important things that heliophysics studies is not just this quiet time behavior, but also what happens when the sun undergoes these periods of intense activity known as solar storms. And during these events, it emits huge blobs of magnetized plasma that distort Earth's magnetosphere even more. Now, here's a video taken by NASA's SOHO mission that shows one of these blobs being ejected from the sun. So this happens when a bubble forms in the turbulent magnetic field on the sun's surface, and it essentially pinches off, where it then flows out with the solar wind, carrying with it a blob of extremely hot solar plasma. Now, Earth is really tiny compared to the size of this blob. And when the sun and the Earth's magnetic field lined up just right, the field lines connect to each other and they change the configuration of Earth's magnetosphere and allow that hot plasma to enter Earth's atmosphere by flowing down the field lines. Now you can see here's the aurora. Again, this is actual video of the aurora at these northern latitudes. And this is essentially a especially beautiful manifestation of this so-called space weather. And it's emitted when the atoms and molecules in the atmosphere collide with those energetic charged particles that are flowing down along the field lines. Now, the moving charges in general constitute electric current, and the storm-induced currents in Earth's magnetosphere flow around in a loop, just like an electrical circuit that's carrying power to your house from the power generation station somewhere else in your city. Now, when that current passes, the current closes in the Earth's atmosphere, it can actually cause a lot of damage to the Earth systems. And so this is what's known as space weather effects. Some examples of these are direct hits on spacecraft and astronauts in orbit. They can damage both the electronics as well as human tissue. They can also, the currents can disrupt radio communication signals. So when you use your GPS system for navigation, for example, or you've had the tractor here using it for its navigation purposes and harvesting the fields, it can lose lock, and essentially you get major errors in your positioning. It can even pass through airplanes. And so the effect on both avionics as well as the human passengers means that a lot of planes that are flying on these polar type trajectories have to divert and change course during solar storms. And then one of the most dramatic effects is what happens when there's an ionospheric current. So this is the ionosphere, is the charged layer of the Earth's atmosphere that carries these currents. What happens when those currents get induced in the ground? They can be picked up in power lines and essentially can short out and cause major, major blackouts. So one of NASA's major goals is studying how this process takes place, how the Earth recovers, so that we can better predict and therefore mitigate some of these most harmful effects of these solar storms. Now, recovery from storms requires that you have to dissipate the energy of those charged particles that are carrying the currents. And the way that this is done is through what's known as charge exchange. When an ion, one of these really energetic, fast-moving ions, passes close to an atmospheric neutral atom just kind of hanging out in the atmosphere, it's slow, it's cold. The electron from the neutral jumps to the ion. And now that neutral atom is hot, and it essentially flies off and escapes Earth's atmosphere. This is, of course, a way that Earth's atmosphere evaporates into space. It's still a very slow process. But ultimately, that ion becomes slow and that current dissipates. Now, the figure here on the left is showing approximately what altitudes this happens. So you can see the ionosphere has its peak densities is where those currents flow between roughly 100 to 300 miles above the Earth's surface. And that ionosphere is embedded within the neutral atmosphere. So the troposphere at the bottommost layer, that's where all the weather happens. Stratosphere is where you see some thin clouds. You've heard of probably stratospheric cirrus clouds. That's also where airplanes fly. The mesosphere is the coldest atmospheric region. These layers are defined by the temperature in each region. And then outer space is typically denoted roughly above 60 miles. So this is where satellites orbit. This is where the International Space Station exists. And then this is a region known as the thermosphere. Now, the region that the Carruthers Geocorona Observatory will study is this topmost region known as the exosphere, and it starts around 400 miles. Now, there's hardly any figures that exist that show the full extent because, as I said, it's huge. It actually extends out to at least 100,000 miles, and if I were to draw it on the same scale, it would be roughly half a football field relative to the size of my computer screen. It's huge. But it's in the exosphere and the neutral atoms in the exosphere where the collisions with these ions do the most good as far as storm recovery. But one of the biggest unknowns is that we don't really have a lot of data that tells us how big is the exosphere? What is the density of the exosphere? What shape does it have? How does it change when these storms hit? And so that is the science goal of the Carruthers mission. Now, the way the Carruthers mission is going to work is that we can't just get up there and start counting the atoms in the exosphere. It's much too big for that. And so we use what's called remote sensing. So just like the aurora is the light that's emitted when these collisions take place, air glow actually happens all the time. Aurora is very special. It happens during storms, special processes. These electrons coming down the field lines are what creates it. But collisions happen among atoms in the atmosphere all the time. And there's other ways of creating essentially the light. And you can see here that they form layers in the atmosphere. Green is below red, and UV stands for ultraviolet. And here's a video of aurora being taken from the International Space Station. So here it is in orbit. It's around 400 miles altitude above the Earth's surface. And you can see the atmosphere essentially glows all the time. This is not aurora. This is air glow. And the Carruthers mission is going to be launched into space, and it will measure the air glow that's being emitted by the exosphere, this outermost atmospheric layer that exists far, far above this red air glow layer that you're seeing in this movie. Now, I want to talk a little bit about how this light's created because that's important to how our mission works and what's so special about it. So essentially, light is emitted by atoms when an electron that's orbiting the nucleus of the atom, it exists in a high energy state. Collisions can put it there, for example. And then when it relaxes down to its lower energy state, what's known as the ground state, a photon is emitted. And the energy of that photon, in other words, its color, its wavelength, its color, its energy, all of these words mean the same thing, directly corresponds to that change in energy between the states. And each atom has a unique distribution of electrons, unique energy levels that they can populate, and therefore unique changes in energy that correspond to unique colors. And so the pattern of the colors is essentially an optical fingerprint that distinguishes one kind of atom from another. And so you can see essentially this is what's known as the spectrum. This is the principle behind optical spectroscopy. So sodium Na is the chemical symbol for sodium. You can see it has these two really bright, these pairs of yellow lines. If you've ever seen a sodium lamp, these are usually used for old street lights. They kind of glow yellow. Well, this is why. It only outputs primarily yellow light. Hydrogen is the next one down. This is the atom that most populates the exosphere, and this is its visible spectrum. Some of that red emission you just saw on the previous slide comes from this red line hydrogen. And then here's calcium and mercury. Again, mercury lamps are often red to orange. But basically, you can distinguish different chemicals by looking at its optical fingerprint, or you can put a filter on your camera and just target the one single color of photons. And that's what the Carruthers mission is going to do. And we're targeting hydrogen. Now, before I go into that, this is essentially what kind of information you can learn by looking at the same object using different optical filters, targeting different chemical transitions, electronic transitions that give off different colors of light. And so this is the sun as seen in all of the different filters that NASA uses to observe the sun. In some filters, like the background one where it's kind of orangey, you can see that sunspot down. I don't know if you can see my cursor down at the bottom there. This is where those field lines essentially pinch off from. But that's what would be a visible spectrum. This is our sun in the sky. It looks yellowish orange. But in different filters, you can see different structures. And some of those structures, you can see essentially those filaments, those loops of the magnetic field, especially in this orange one that SOHO acquires. Now, I mentioned Carruthers is going to be looking at hydrogen, and the reason for that is that it's really perfect for exospheric sensing. First of all, it's the lightest atomic element. It's got one proton and one electron, and that means it's lighter than helium, which has two protons, and which means, everybody knows helium balloons float up naturally into space because they're so much lighter than the air around it. Well, hydrogen's even lighter than helium. And so it floats up. And so that topmost, outermost atmospheric layer is comprised almost exclusively of hydrogen. It dominates exospheric composition. And because it only has one electron, it has the simplest spectrum. It's got very few emission lines because the electron doesn't have that many options of jumping between the different energy levels. So the figure over here is showing all the different transitions, every transition the electron could possibly make. N equals 1 is that innermost ground state. And if it gets excited to N equals 2 and then relaxes down to N equals 1, it gives off the brightest air glow line in the whole solar system. It's even got its own name. It's called the Lyman alpha line. And I've shown it here in this hot pink color because 122 nanometers is actually in the ultraviolet portion of the spectrum. Ultraviolet, you can kind of see it sometimes when you shine a black light on something. If you've washed your clothes with bleach, the bleach fluoresces in the ultraviolet and it kind of glows. Sometimes your teeth, the fluoride in your toothpaste will make your teeth glow extra white under black light. Black lights are cool, but this ultraviolet line is the one that the Carruthers mission is targeting. Now, the problem is that ultraviolet emission is really hard to measure. First of all, the Earth's atmosphere absorbs Lyman alpha, so you have to get well outside the atmosphere before you can detect any of these photons at all. Secondly, they don't interact with a camera the same way that visible photons do, red, blue, green. I've got my cell phone camera. It detects colors, but it only detects colors in the visible portion of the spectrum. It's not sensitive to ultraviolet photons. It takes a really special kind of camera in order to detect those. And then the biggest problem by far, the reason that we hardly have any images of the exosphere at all, is that, as I mentioned, the exosphere is huge. It's too big to fit in a single image unless you have your camera really, really far away. Well, that problem of having it be hard to detect was solved by a man named George Carruthers. He invented the technology that allows pictures to be taken of ultraviolet photons. And he did this. Meanwhile, he invented the camera. They say, where are we going to put this camera? Well, he invented it in the 1970s. The lunar program was in full swing, and this is where they put it. Apollo 16 astronauts brought his camera with them. They deployed it on the moon. Here it is, his gold-plated, famous Carruthers camera. Took the very first image of Earth in this ultraviolet emission. And in fact, what's really cool is that the astronauts didn't bring the camera home with them. They only brought home the film cartridge, which means that telescope, that camera, is still sitting on the lunar surface today. Now, here is Dr. George Carruthers. He's posing with the ground instrument. They built two. You almost always build two. One is for ground testing. You take the one up on orbit. If it starts acting funny, you deploy it in space. If it acts funny, you can try to experiment with its identical twin down on the ground. That twin instrument is now on display at the Air and Space Museum in Washington, D.C. I encourage everyone to go see it. And then the middle photo here is of Dr. Carruthers posing with the actual film canister that the Apollo 16 astronauts brought back with them. And then finally, the picture on the right is the actual photograph that he observed. So this was the first hint that people had about just how big this glowing atmospheric region really is. Now, in this picture, it doesn't really do it justice because the camera wasn't that sensitive to the faint emission that occurs in the outermost extent. Since then, NASA has learned that it extends almost halfway to the moon, but NASA's only ever taken, apart from this one, 2 other photographs. And so what our mission will do is build on this legacy using almost identical technology as to the camera that Dr. Carruthers invented. We'll build on this technology and we'll be deploying it in space where we will take routine images of Earth's exosphere so that not only do we get it all in one field of view, but we get to watch it as it evolves over time. Now, the NASA had this great idea back in December 2022 to have our mission really honor his legacy. It's not just that our camera was designed after him, but this mission is Illinois' first NASA mission. No one in Illinois has ever led a NASA mission before. And it turns out, by coincidence, maybe or maybe not, that Dr. George Carruthers is a 3-time alum of the University of Illinois at Urbana-Champaign. And the coincidence just seemed too good to pass up. And so in December of 2022, NASA renamed our mission. The original name that we had given it was GLIDE, Global Lyman Alpha Imager. Lyman Alpha, remember, is that line, that color line in the ultraviolet that we're going to be taking pictures of. Imager of the dynamic exosphere. We're getting movies of it for the first time. They changed our name to honor Dr. Carruthers, and so we're now known as the Carruthers Geocorona Observatory, and we couldn't be more proud. So the other special thing about our mission is that we're not going to be deployed to the moon. We're going to be deployed to the perfect vantage in space. Even the moon is a little bit too close. And meanwhile, the moon is orbiting the Earth, and part of the time the sun is visible behind the Earth, and that would really mess up our pictures. We want to have the sun behind us when we take the pictures so that we can turn around and just stare at the Earth all the time. Well, the perfect place for that in space is what's known as the L1 gravitational equilibrium point. So what I'm showing here, imagine gravity being a big rubber sheet, and any object that has mass is essentially going to deform the sheet and have it essentially bend down and have a little dip where that massive object sits. The bigger the mass, the bigger the hole that it's creating in this rubber sheet. Well, here's the sun with its really deep, this is essentially potential energy. It's a potential energy well in gravity. Here's the sun, really deep hole. If something were to get captured by the sun's gravity, it orbits the sun. In fact, that's exactly what Earth does. It orbits the sun. The moon, on the other hand, is captured in Earth's gravity, so it orbits the Earth. Well, about 1 million miles away from Earth, directly along the line connecting Earth and sun, is a gravitational equilibrium. Earth's gravity pulls just as much on that point as the sun's gravity does. And it's really easy to essentially put a spacecraft there. It doesn't have to do much in order to maintain that location in space. And this is what's known as the L1, named after the famous French mathematician Lagrange equilibrium point. Now, here's a video of our orbit that really shows just how far away from Earth and its magnetosphere that we're going to get. The little green plus there is the L1 equilibrium point. As I mentioned, it's about 1 million miles away from the sun. It's about 1 million miles away from Earth. Earth is drawn to scale in this picture. You see how tiny it is. And then that big gray shaded zone, that's the magnetosphere. The exosphere extends well beyond the outer bound of the magnetosphere, but again, we don't know exactly how big because we've only ever had 3 pictures of it. We don't know if its shape and size changes dramatically over time or not. But that's exactly what we're going to find out. By the way, the little thing orbiting the Earth there, that's the moon. That's the lunar orbit. So the moon comes in and out of the Earth's magnetosphere, and we are 4 times farther away from Earth than the moon is with our orbit. We're going to be hanging out. Each period of this orbit is 6 months. Our primary mission is 2 years. And then we have propulsion. We have a big tank full of hydrazine, and we can shoot shoot the propulsion out the thrusters on the side in order to maintain orbit. If we start to drift off, we get ourselves back into position. We have enough orbit to hang out here for 10 years, at which point we run out of propulsion, and then we'll go into orbit around the sun, where essentially we'll live for the next billion years, 2 billion years. I mean, it would literally take an asteroid hitting us to destroy our mission. It's going to be a very, very long-lived piece of hardware. Okay, so here is what our camera will be observing. So that big sphere is the full extent that we expect the exosphere to have. That sphere extends halfway to the moon. And then our cameras we got 2 cameras. The blue box demonstrates the field of view of what's called our wide field imager. We'll take a wide field image every hour. And as we transit on this orbit around L1, we maintain pointing back at Earth the entire time. So we'll slew off nadir to take some, calibration data, look at some stars, calibrate the instrument and whatnot. But most of the time, we'll be getting an image, wide field of the entire exosphere every single hour. But then meanwhile, we also have a narrow field imager. So the 2 cameras are aligned. It's called a nested field of view. But that narrow field imager essentially has a higher resolution, and it's really zoomed in on the middle of the Earth. Off to the left here, you can see what we expect our sample images to look like. This is based on a modeled exosphere. We pass it through another model of our camera. You can see the Earth is very, very tiny in the top picture. That's the wide field imager image. And then the Earth, this yellow ring is the brightest emission before it gets absorbed by the Earth. So it's getting absorbed inside that ring. That's roughly where the Earth's surface is in that bottom image. Now, what are we going to do with these images? Essentially, we've got this time series of 2D images, 2-dimensional images of this ultraviolet Lyman alpha emission brightness that's being emitted by Earth's upper atmosphere, its exosphere, its geocorona. We will use those to derive using physics-based models. Essentially, this is why I'm in the Department of Electrical Engineering because this is a pretty tricky signal processing problem. But we're going to turn those 2D images of the emission brightness into the underlying 3D density distribution of the emitters themselves. And we're especially looking for spherical asymmetries. We're expecting them to be along the sun Earth line, so essentially a noon midnight asymmetry. That's where the solar wind is pushing on the Earth and generating essentially that perturbation in the magnetic field that I showed earlier away from its dipole configuration. We expect dawn-dusk asymmetries because dusk tends to be a lot warmer than dawn as the Earth is spinning. Dawn is really cold. It's coming out of nighttime where the atmosphere hasn't been illuminated for very long, whereas dusk, as it's spinning, has been sitting in the sun all afternoon. And then we don't know if we'll see north-south asymmetries or not. It will be surprised. And then the movies you're looking at here are what density might do. This is a model simulation that was run by a colleague of mine, Hyunju Connor, what the densities might look like as a function of time on our hourly cadence. And then the next sequence of images right here this is what we expect it to look like during a geomagnetic storm. Huge, huge changes. And we'll be able to watch these evolve as movies and really gain a lot of knowledge then about how the Earth responds to these storms. It'll improve our model forecasts, as well as our ability to really protect both humans and our technological assets from the most harmful effect of these space weather events. We will be launching in 2025. I'm super excited. And we're using the biggest rocket in SpaceX's fleet. This is a partnership that NASA's made with the company SpaceX. What you're looking at here is its full thrust Falcon 9 heavy rocket. That's going to be our launch vehicle that's going to get us as far away as we can get, right? This is a deep space launch. They don't make these launches very soon, very often. And I can't wait to come back after we're on orbit and share some exciting science with you about a year from now. Thanks very much. I'm welcome to take questions.
Thank you, Laura.
Sure.
Certainly is an exciting mission. And so we've got several questions now. And again, I'll remind folks that if you want to ask additional questions, please do. Let's see, I think I'll organize the order in which I'll ask questions. I'll start with ones that are most directly related to the mission, and then there's some additional questions about, getting into being a scientist that we can talk about in a little bit. But let's see, one of the first questions is from Jason, who is asking about he recently had read that the magnetic North Pole of Earth has been drifting over time, and he wonders how that kind of change in Earth's magnetic field affects geomagnetic storms and whether or not it influences the exosphere at all.
Oh, that's a really fantastic question. It absolutely affects geomagnetic storms. So as the pole drifts, the location, the configuration of the magnetic field in the outer magnetosphere, or even the middle magnetosphere, changes. And so when those field lines reconnect, I can go back to that movie. Almost there. Right here. No, one more. When the field lines reconnect and they drift around and that aurora flows down those field lines, it traces out an auroral oval. Well, when the pole drifts, that auroral oval changes its location. And so one of the things that's really impacted the heliophysics community is the fact that ground stations in particular, which used to be at what we considered mid latitudes, they were never in the auroral zone before, such as there's some in Massachusetts, a facility known as Millstone Hill, is now in the auroral zone quite often. And then facilities that were deployed in order to measure aurora now no longer do because the aurora is not overhead. And so that change in configuration is definitely something that's being affected by the migration of that geomagnetic pole. Now, the exosphere itself isn't that much affected because the exosphere is neutral. Neutral atoms aren't affected at all by magnetic fields and electric fields, whereas any kind of a charged particle, an ion or an electron, experience forces associated with those fields. So the exosphere kind of still does its same old thing, but because the plasma environment adjusts to the new magnetic field configuration, that charge exchange process that I mentioned, that is affected. And so that governs, essentially changes Earth's recovery from these storms. And so that's something that's definitely needs to be and is currently being accounted for in some of these predictive models. But it's very difficult to predict where the pole is headed and how fast it's going to move. It's right, just in the last 10 years, that migration of the pole has really accelerated unexpectedly. And so it's not something that we can really predict, but it's certainly something that NASA's monitoring and folding into its models on a real-time basis. That's a great question.
And there's another question from that Carol asked, which is related. She was wondering, is it true that the Earth's magnetic field flips? And when it does that mean that Earth doesn't have a field? And what's the timeline? When might another flip occur?
That's a great question. So let me back up and say that flip, we don't know a lot about that flip. Now, the sun's magnetic field, when we say flips, the North Pole and the South Pole reverse direction. This happens on the sun, this whole cycle, it flips and then flips back every 11 years. And during the maximum, the period when it's kind of in the middle of a flip, that's that active period that's producing all these storms. That's when the magnetic field gets very turbulent and some of it pinches off. Those are those storms that I showed you. Now, Earth's magnetic field, there is evidence in the orientation of magnetic elements, essentially. This is not my area. This is all pretty much all I know. But if you look at plate tectonics, where the crust of the Earth had come out on the sea floor and spread out, you can see stripes where the magnetic orientation of the rock particles reverses direction. And it's clearly had multiple cycles. Now, geologists estimate that that reversal takes place once every 750,000 years, if I recall correctly. Again, this is not my area. I think it's been 600,000, 700,000 years so far. But I wouldn't say that it's imminent or anything like that. I certainly haven't heard anything that it's anything we need to worry about. Now, as far as whether or not the Earth's magnetic field, when it does this flip, will reduce to zero and therefore leave us exposed to solar wind before it reverses and kind of builds back up again with the reverse polarity, it's unlikely. Because if that were the case, then you would have expected a lot of the atmosphere to be blown off, whereas Earth still has lots of its atmosphere after multiple reversals. Mars, for example, doesn't have a magnetic field to shield it from space, and it hardly has any atmosphere at all. And so my understanding, again, this is not really my area, but my understanding is that Earth will stay protected. The magnetic field strength will be sufficiently strong to still maintain this magnetospheric bubble that protects us from space weather during the transition. Whether it's imminent or not, I think that would be a geologist's, you need to get a geologist to answer that question.
Thanks, Lara. I can add a little bit of what I know about that is even though the average time between flips is like, as you said, about 750,000, there's been period, like that's the average mathematically, but there's been periods where it was stable for tens of millions of years,
Ah, okay.
periods where it actually flipped, every 10,000 years or so. So it's like, it's really very,
Chaotic.
it's kind of chaotic. Yeah.
Yeah.
Difficult to
Yeah.
predict. Yeah.
Yep.
So I'm going to ask kind of two questions because they're somewhat related. So, one attendee is asking about 2025 and whether or not we are expecting very big solar storms in that period. And another person had asked whether or not the timing of the launch of the Carruthers mission was timed with the solar cycle at all, so that we're launching right at or just after the maximum.
Yeah, again, great questions. And the answer is absolutely yes. This was very much planned. But then again, it was also something when I say it was planned 8 years ago, back when it wasn't even close to solar maximum. So, solar maximum, if I'm not mistaken, NOAA just declared peak less than a week ago, I think. So we're right in the maximum cycle. So this is again the solar uh, periodicity, this 11-year solar cycle where the polarity flips of the sun's magnetic orientation goes through this maximum activity phase where a lot of storms are generated, and then kind of a quieter minimum phase. Maximum is happening more or less this year, late 2024, early 2025. We're definitely launching in a window in which we expect to have several years of plenty of storms to observe hit the Earth. Now, when I say we timed it, we knew that our launch would be in 2024, 2025 time period. And we were interested in studying storms, but it's a confluence that we took advantage of, so to speak. Back when the solicitation for these missions came out for us to write our proposal, we noticed that the launch would occur during solar maximum, and therefore targeted the science to those solar storms. So yes, not a coincidence, and it's something we're extremely excited and looking forward to.
Awesome. And I think one of the questions was specifically, is there going to be a big storm in 2025?
I hope so. Again, it's not something you can predict. Just like the Earth's flipping is a chaotic thing, the whether or not a given substorm pair is going to produce one of these bubbles that pinches off or not, whether that bubble, even if it is created, that gets pinched off and flies off, whether it's on a trajectory that it's going to impact the Earth. If it does impact the Earth, is the field line configuration going to be such that reconnection occurs? All of these are open questions, but statistically speaking, it's highly probable that there will be a big storm in 2025. Already, the first half, the leading, ramping up to the solar maximum phase that we've seen just in the past year, has yielded some of the biggest storms we've seen in a very long time. I know personally, I'm here in central Illinois. I was able to see aurora and take pictures of it using my cell phone from my backyard not that long ago. That was a really big storm. The auroral oval essentially moved outwards and downward in latitude, which is what happens during these big storms. And we do expect that the second half of solar maximum would be a similar strength to the first half.
We saw them in California too.
Did you?
So it was fantastic.
Very
I believe
exciting.
in the
Yeah.
Bay Area, I got a cell phone picture of the aurora.
Wild. Yep. Doesn't happen very many solar cycles. You have to wait usually 20, 30 years to see something like that
You're lucky.
in your own location.
Okay, let's see. There's some other good. I want to jump to one of the questions that's kind of about science. There's people who are interested about working for science, and they're kind of wondering, like, how can I work for science? How could I join NASA?
Ah, uh, you know, uh, NASA has so many different disciplines actually that it supports. So, as far as choosing a major in college or even what classes to take in high school, math is always a really good one. If you want to do the actual science work and make contributions in a scientific way, almost all disciplines use some math. That being said, physics, biology, chemistry, these are all domains that NASA supports. So, for example, I mentioned back on my fleet chart picture, let's see if I can go back there. These orange ones are things like chemistry and biology and physics. How do bacteria grow in space, for example? That would be a biology domain, microbiology maybe. How does the human body respond? Humans in space is a completely separate, that's not really science mission directorate. But nonetheless, the science of that is definitely something that you could do within NASA. If you want to do something like what I'm doing, which is remote sensing, my background is primarily in physics and astronomy. And then now I've found my way into electrical engineering. I don't actually have any degrees in electrical engineering, but at the University of Illinois Urbana-Champaign, one of their specialties, so to speak, is this field called remote sensing and space science. Different universities have it in different departments. My personal alma mater, Boston University, had it in the Department of Astronomy. Michigan has their own department for it because they're so strong in that area. Sometimes it's in aerospace engineering. That's another big one that would allow you to work for NASA. They hire a lot of aerospace engineers. But as far as high school, take some physics classes, chemistry, biology, math, and see what you think. Another career opportunity for NASA, if you didn't want to actually contribute to the science yourself, writing proposals, doing the data analysis, building the instruments, and that kind of thing. NASA also employs a lot of journalists and graphic designers that make the videos to convey the knowledge that's been gained. And so all of the videos and the vast majority of the figures I've shown in my talk, for example, are made by NASA by people that don't necessarily have physics degrees, but they do have a strong interest in science that's been, demonstrated and so on. But they possibly majored in communication, for example, or graphic design and that kind of thing. So NASA, it's a huge organization, lots of room for lots of different kinds of careers.
Awesome. Thank you for that. One thing I always like to tell students too is that there's opportunities to do internships all the time, and you
True. Yeah,
never real you never really know whether or not you're going to like something unless you do it. And so these
that's right.
internships are a great opportunity to crack, get your hands dirty and see if you like this kind of stuff.
Yep. Yep. Absolutely.
Let's see. Here's an interesting question. Someone's curious about like what were the biggest challenges that you faced while developing the Carruthers mission?
Oh, that's a great question. So our mission, I'm going to go back and show the picture of it. One of the really neat things about our mission is that it's what NASA likes to call low risk. So for example, the mission concept is really simple. We're going to point our cameras at the Earth. And then meanwhile, we've got our solar panels on the backside, and they're sitting there staring at the sun all the time. We get all the power we want, right? Easy. Even the thermal gradients, which are something that's really hard for Earth orbiting missions to design around. They're on the day side and it gets really hot, and then they're on the night side and it gets really cold, and they're constantly cycling through thermal cycles. Ours doesn't even have that problem. The sun's always on the same side all the time. And then meanwhile, our instruments and our spacecraft bus, as I mentioned, they have a lot of heritage. I mean, the camera itself was originally based on a design that's more than 50 years old at this point. Now, that being said, every mission has challenges. One of the biggest challenges that we faced was early on. It was in the proposal phase. And that's because the way that NASA missions get awarded is they put out a solicitation. And in our case, the solicitation came out in 2018 that says, hey, we have an opportunity to give you a ride. This is essentially what our solicitation said, to give you a ride on this gigantic rocket and drop you off really far away in space. Well, a solicitation like that only comes around once every 20 years. And I said, wow, we need to get there so that we can take these ultraviolet pictures and study the exosphere. This is a perfect golden opportunity that doesn't come around that often. And so we put in our proposal, and then and lots of people submit proposals. And then what NASA does is they usually pick two or three to then compete against each other. And you have to write a much bigger proposal. In our case, it's called a concept study report. That second round of proposals, ours was 1,006 pages long. Huge, massive document, had color fold out pages, glossy, hardbound, spiral bound book. Um, we ended up getting selected on the basis of our concept study report, but the concept study report was due in June of 2020, right after no one's allowed to leave their house. My kid was doing kindergarten from home on Zoom. It was a very, very difficult time for everybody. And so for us to be able to pull together and put together such a compelling second round proposal is something that I'm very proud of. That was by far the most challenging aspect of the project, and it wasn't even really project related. We've been very fortunate that the project itself has had very little technical issues. It was more the logistics in the beginning of getting it off the ground.
That's a really good perspective to give folks. Yeah, that process, especially under such a
A
interesting.
lot of time, a lot of time on the phone. Yeah, I tag teamed the Zoom kindergarten because it was my Zoom link with my own Zoom meetings, and every 10-minute gap was a bunch of sit-ups and jumping jacks for my 6-year-old.
Nice. So actually, though, from the conception of the mission to kind of its end, another question we have is, so once the fuel runs out and it's just out there orbiting the sun forever, is there still science that you can be doing with it?
That's a really good question. Assuming our cameras work, the big problem with it is going to be that it's too far away to be able to communicate. So our communication is two ways. First of all, and we use, by the way, we have to use the biggest ground-based telescope network on Earth. It's managed by the Jet Propulsion Lab, known as the Deep Space Network. This is the system of telescopes that talks with Voyager, which is 1 billion miles away. It talks with all the planetary missions and communicates with them. Ours is far enough away that we need the Deep Space Network for that. Now, Deep Space Network is sensitive enough to talk with satellites that are very far away, provided that they have enough power and a big enough antenna that their signal is strong enough to detect. Ours isn't. This spacecraft, I didn't mention it, our spacecraft is about the size of a dishwasher. And our antennas, are a little tiny piece of that stuck on the side. They're on that camera facing, earth facing side. Our antennas will not be sufficient, and the amount of power our solar panels generate will not be sufficient to be able to talk to it when it's in orbit around the sun, except for maybe when it comes back around and it's kind of near L1 again. But there's no telling what its orbit might actually look like. It might end up having a pretty, it might get pulled in really close to the sun, in which case it's a lot further from L1 at that point, and we'd have no hope of being able to downlink the data that it might be acquiring. So it's a good question. I hope so. We'll look for it and it's got a little radio beacon. As long as we can detect its little radio beacon, we might be able to track its trajectory. But once it goes behind the sun, I think it's unlikely they would be able to spot it when it comes out the other side. That doesn't mean it won't be there. It'll be there in my heart and in my mind, in my imagination.
I always imagine future space tourism where, we can go and kind of visit the ancient history of humans' early attempts, and we can fly by and, oh, here's, the Carruthers mission that was launched 100 years ago in 2025.
Yeah, yeah. Well, my first stop would be right there.
Oh,
That
yeah.
Apollo 16 camera. I mean, what fun that would be to go back to the surface of the moon and it would still be there looking exactly like this. I don't even know that it would be dusty because there's no atmosphere to really blow dust around.
Well, I think we've probably got time for maybe one, at least one, maybe two more questions. And so, I am going to pick one that is about that camera. And so someone is asking if you could explain the mechanism of how that camera detects UV and makes an image with it.
Oh, that's a fantastic question. Okay, so this uses a principle called the photoelectric effect, which Einstein discovered and won the Nobel Prize for. So the idea here is that an ultraviolet photon has such high energy, right? If you go back here, this Lyman alpha photon, for example, in general ultraviolet photons, the change in energy between n equals 2 and n equals 1, it's not drawn to scale. It's so big that the wavelength is so tiny, the energy of that photon is so large that if you just shine that ultraviolet light on a regular camera, it goes right through it. It doesn't actually change anything on the surface of the camera that you could detect. And so instead, what we do is we don't shine it on photographic film or anything like that. We shine it on a very special metal. Uh, it's made of potassium bromide. And when you hit it with a really energetic photon, it releases its own electron. So this is what's known as the photoelectric effect. And then we essentially count those electrons. We steer them down an optical path in a sensor, and then we have them hit what's known as a phosphor screen. And so phosphor screen does the opposite. When an electron hits the phosphor screen, it gives off a nice green visible light photon. And then we stick a typical camera, just like the kind you have in your cell phone, more or less, that then counts up those green photons. Now, at that point, they're all the same color, right? So we basically turned a Lyman alpha color photon into a green photon, but we're able to count the number of photons, in other words, measure the brightness of that Lyman alpha line. And that leveraging the photoelectric effect for this detection, together with how you steer those electrons down so that you can focus them into an image, those were Dr. Carruthers' major contributions to that concept. That's a great question. Thanks for that question.
Yeah. All right. Well, we've hit the top of the hour, and so I want to respect everyone's time, and I want to thank Dr. Waldrop so much for discussing the mission and sharing everything with you. There were so many questions. Thank you all so much for all of your questions, and we didn't get to all of them. You can ask your questions of our scientists who are standing by to answer on our Discord server that's on the Space Weather Explorers Week website. And in fact, let me just put up our final slide here so that we can be reminded of that. Let's see, are folks seeing the screen? Yeah, so you can go to spaceweather.ssl.berkeley.edu. You can ask more questions, and some of our scientists would be happy to answer more of your questions about space. There was a lot of great questions about that. And in fact, tomorrow's theme is all about space careers. So if you're really interested in becoming a scientist or an engineer or an artist who works for NASA, come and ask your questions about that, and we'll be happy to share what we know in our own experiences. There's videos on the website as well where you can hear different space scientists talk about their careers. And please fill out our survey to tell us, how you like this webinar and are using the website. That really helps us figure out um, how we can make sure we keep doing this. And we'll be having more webinars like this. You can bet that we'll be having some webinars right before we launch next fall. And so if you want to learn more about the mission, come back and join us then. All right, so
Thank
thank you all. We'll see you again in Cyberland. And until then, watch out for those space weather reports.
Thanks, everybody. Have a great day.
Everyone.